Well, welcome everyone. It's 11 o'clock. We'll get started. We have an exciting agenda here for today, focusing on air quality in rural areas. And our first speaker is a HAQAST member, Amber Sawyer, from the National Institute of Aerospace, a resident at Langley. And over to you, Amber.
Thanks. I'm going to try to keep this within 10 minutes and hopefully we'll have a vibrant discussion afterwards. So everyone on here contributed. So at some point in time, before, during, after conversations, they might not even have known how much they contributed. So one of my main points is going to be not all fire is bad. We always think of it as bad and poor air quality, but it isn't. In order to prevent the bad fire days, we have to have more good fire days. And that's just our reality as weather and climate change. That's going to be our reality. So fires are good in that it can cycle nutrients. We can select for the flora and fauna, the species we want on the landscape. We can choose endangered species. It resets the succession of particular ecosystems. Ecosystems, every one of them evolved with fire. So we need fire on our landscape. We are on fire's turf. Fire isn't on our turf getting in our way. So those are the reasons that we need to have more good fire on our landscape. That's one of my major points. So we decided as a big group, a wonderful Tiger team, and I want to thank the leadership there. I don't see them in here, but I mean, the Tiger teams are just awesome, in my opinion, getting to work with so many diverse people. So what we decided to do is look at the Flint Hills and in the Southeast, and our larger investigation is in the Southeast. And sometimes the Southeast is dismissed, and it's actually, there's a lot of fire there. And if we look at a normal fire year, the equivalent is as much as it is in the West. The difference is they burn more all the time, so it's more in control, doesn't get out of control. You don't hear as much about it. And small fires, as we've heard, are really challenging to see because they're not burning over at the time polar orbiters are overhead, and they're small. They can be understory burning, and so we don't see as many. So we've got to think of a different way to quantify our error in that. And if we don't get that right in the emissions inventory, then we don't get health studies right. So we don't get the rules and regulations right. We have to get emissions right before we can even ask the health questions. What's the difference between a big fire and the big episodic, or the ones that go for 3 months? What are the health effects? As Cheryl said, she needs to do a better job. So I know she's got that in her notes, all by herself. So at first we looked at patterns, and this verifies what we know on the ground. And Emily did a lot of this work, and we know that the largest burning is in April. There's some side seasons in March and May. So it's a potential to extend that season to meet air quality and keep exceedances down, possibility there. And we started to look at burned area. We haven't completed our analysis. So what we're trying to do is put error on this. What are the omission errors? What are we emitting? What are we missing? And so that way we have good error bars on the emissions inventory, which is one way we hope we can help the community. And it's like we thought, you can't see the small fires so much, but you can see all the big fires. And then how good are we at quantifying the area? That's the next question. Pretty good at the big ones so far. So, and that was Emily's talk, so go back for that one. So at the same time, we're looking into this and doing what we think we should do. We hear from Kansas State University and our other partners, and they've said, oh my gosh, this is the dustiest year we've seen. There's lots of droughts and there's wildfires burning, which is different because you don't light prescription fires when there's wildfires burning. And this is their prescription fire season. It was the windiest extraordinary event since 1950. So it was definitely a different season. And this is coming from people on the ground. And so we were at the same time, we're talking to our Tiger team partners. And in the top right, you can see the number of HMS, a NOAA product that is the hand-drawn smoke days. And 2022 is in the far right. So it looks like, well, there are a lot of covered days with HMS smoke in Kansas and the Flint Hills. But if you look at the other years, it's like extraordinary. So, and then we started looking at the HMS smoke plume maps that are on the bottom and the top, and you can see that a lot of the smoke is coming from other fires. There was smoke coming from Mexico, New Mexico, and Arizona, and it's detraining over to the Flint Hills. So it's covering that area. So what we did is we took that smoke out. Next. Oh, I'm saying next slide, please. Never mind. I got that. No, I don't.
Moving now.
It is not. There it goes. All right. Okay, so when we take all the smoke out, 2022 does not look extraordinary. It looks like other years. It's a little bit greater than 2021, but it's about a normal fire year if we take out the smoke that contributed from other regions. So next we decided to look at the vertical, and there were a lot of questions about this yesterday, so we can go into this a little more if you want to, but this is Calypso data, and Calypso is like taking Landsat, the 30-meter data, and turning it on the side. So you're getting a slice of the atmosphere. So what can we see with this type of data? And this was an instrument that's been up since 2006 actually, but the full year 2007. And it was supposed to live for about 18 months. It's still going. It's about ready. It's chugging. It's about ready to go off. But at any rate, it's done a fantastic job. And we can see in the top left, we can see aerosols in orange, and these are clouds in blue. So we can see these large vertical patterns. On the right-hand side, we again have the hand-drawn HMS product that comes at various thicknesses. They dry it every couple hours or 6 hours whenever they get around to it, depending on who the person is. And the black line is the Calypso tract. So that's where we're going over. And the red and blue are fire detections. In the bottom left, we're looking at the aerosol subtype. So if we look at Kansas, you can see, and I'm telling you all this because the next ones are going to go fast, about 35 to 40 is where we want to look for the Flint Hills. So if we look here, this I know is smoke. And the reason I know it's smoke is because I can have ancillary data on the right-hand side. So I would say this is pretty normal looking smoke, maybe a little more dust than usual, but black is the classification of smoke. And then what happens with the backscatter LiDAR is we don't do that great of job at being able to tease this apart. So you'll have pollution and then you'll have smoke, but we can't get that middle part right because it doesn't directly measure the LiDAR ratio. The high spectral resolution LiDAR that's coming in the future. And if anybody has any pull, talk it up with your agencies because it's expensive. It's supposed to be launched in 2028, 2032, but there's questions because it's expensive. But this is the instrument we need to take health and air quality forward. It's one that will actually be able to distinguish the aerosols types well, which is what matters. If we're in marine aerosols, that's different than if we're in thick smoke. And is it at the ground? So this is a tremendous asset. So right now, that is the reason this is different. So this is pretty normal looking to me. Now, if we go to the next one, this is a lot of dust. So we see dust and it's going all the way down to the surface. So all of this dust and smoke is at nose level. So it's covering the area. And if you look at the ancillary data on the right-hand side, there are some fires, but as many as you see the browns and the blacks. So it's about right. So the dust is covering the region. So they're having droughts and dust. Thank you. And here we're looking at a lot of smoke, black and brown at the surface, and dust that's a little bit elevated and some blacks and browns here. So that also is highlighting a lot of dust. And some of it's been transported from Mexico, and you can see the smoke on the right-hand side and the fires on that side. So and this is a little different example where the dust is elevated and we have the smoke signatures at the ground, the aerosols at the ground, where they're breathing and where they're lighting fires. So if we look at this all together, in the top left, we have how many aerosol types are in the potential of that entire column. And we can see that dust is high in 2022, higher than it's been in the record. And in the bottom right, we're looking at all the aerosols and the relative proportion of aerosols, and dust is still the highest in 2022. And the brown is this is going to be a mixture of smoke and dust and smoke. So it's the blacks and the browns. This is a lot of smoke that's in the area as well, and dust. So it's just a phenomenal year. So this is my last slide, and fire and ecosystems evolve together. We need good fire on the landscape, but there are a lot of questions about how we can do this and keep people safe and keep air quality exceedances low. There are some ideas, and we are going to need to take actions at the end as well. So thanks for that, and I think that was it.
Thanks, Amber, for a great talk. Our next speaker is Byeong-Uk Kim from the Georgia Environmental Protection Division.
All right, thank you, everyone. I really like Amber's talk because it kind of set the stage for especially the prescribed burn that I'm going to cover for us. Today, I would like to go over what program and plan that we actually run to take care of the air quality in rural area. Just as a kind of announcement or advertisement at Atlanta for the urban area air quality for our agency on Monday, last month, I guess this Monday, that we are officially now classified as attainment area for the ozone. So in Georgia now we are attaining every single next. That's really good news. It's really big deal for us. Now that still we have still work to do, and one of them is the regional haze. This is about the visibility. And I'll go over a little more geared toward the permitting side of the story, where we have a program called the PSD, Prevention of Significant Deterioration. And then I will go back to, as a sort of continuation of the Amber's talk about prescribed burn and the relationship to our PM2.5 management plan. And the last bullet is really my sort of wish list for the satellite community. I would like to have this data if we have all the money and all the efforts and everything. So there. All right, regional haze. Basically, the Clean Air Act defined the something called the Class 1 area. It's basically that we want to have pristine air on this area. Most likely, these are national park and things like that. There is a predefined. I believe there should be some number that I can read it now. There's over 100 some national park, and then 2017 regional haze rule basically saying that. When you have a really bad visibility, that still you need to be under certain expectation that's set by a regional haze rule. That's what we work on every kind of every 10-year cycle to come up with a modified plan and or revised plan to meet the ultimate goal that's a 2064. So here is a one site stand in Georgia that we show. Here the graph shows the x-axis year and the light extension. I know that you guys like the equations, so and the audience in the online. So I put the equation here. How to come up with this beta extinction or light extinction calculation out of the PM2.5 component. Bottom line story is that we worked on a lot on reducing SO2, which has been a big component for our visibility issue. And then that formed, SO2 in the air, oxidated, and formed the ammonium sulfate, and has been dropped a lot. That helped us to get the light extinction downward trend. And this is another site at Okefenokee Swamp in the southeastern part of the Georgia. And then, sulfate and SO2, because once you form the sulfate, there is no turning back. It's an irreversible reaction. So it's a pretty good case where you reduce the direct emission, that you got the really good air quality improvement, and there is a really good correlation. Has a little different story for the NOx, that nitrate, as you may know, that it can evaporate out of the ammonium nitrate depending on the condition, so that oftentimes you even have a little unwanted trend like this. So this is possibly the kind of next round of the next round that we need to work on a little further. So, all right. Speaking of which, I guess you keep hearing ammonium sulfate, ammonium nitrate. So where is the ammonium coming from? That's ammonia in a gas phase. So now the question is going forward, is ammonia going to be the limiting factor for this, or is it going to be NOx, given that the NOx start getting lower and lower and lower? So that's a kind of question. And you can kind of imagine that one of my wish list is the ammonia measurement out of the satellite. So I kind of give a heads up that the PhD program, it's really multiple, but bottom line is when the Clean Air said back in like 1977 or so, it basically says that, okay, you have a class 1 that's really pristine air supposed to be, and then everything else was supposed to be class 2 or class 3, but nobody ever claimed that we want to be class 3 so far, as I know. So everywhere else in the United States is class 2. So meaning that you have a little bit of room to grow, but let's keep that not really up to the neck of the next. That's a basic idea. So it's called the increment. So the PhD program is basically saying that, okay, you can build a new emission source and everything, but not over to the point that it's further deteriorating air quality in that area. So that's basically the program of it. So to do it, we got to do the numerical demonstration of, okay, if the company or factories built there say that their potential emission is like 100 tons per year, then still the area should be meeting the NAAQS and everything. And to prove it, oftentimes we not just demonstrating the source contribution, but also we got to add the background concentration and things like that to see if that new permitted source will not really deteriorating or exceeding NAAQS. Unfortunately, you keep hearing about the network, I guess, abundance in terms of ground monitors, that we don't necessarily have all the monitors that we want to have nearby. So we come up with some idea of the regional representative monitor, but it would be ideal or desirable to have actual number at the site for the better in the form of NAAQS, like 1 hour NO2 we've been talking about in terms of NAAQS, it's actually 98th percentile and 3-year average and stuff. So that's kind of what we're hoping that we can get out of satellite data in the future. And switching gear to the PM2.5, specifically in a rural area, this is the extensive report that we've been working on. This is 1 page of it. We basically put together every data that as much as we can. As you can see, it's very busy slide. Basically, we have a high-speed trajectory for the hours that's over. In this case, 35 micron per cubic meter for given hour, because most likely right now as a daily extent, we are focusing on daily standard. And then we have average concentration of the places. Here in this case, it's 38, so it's exceeding. It's not violating technically, because violation, again, you got to come up with the calculation that's following the next form. But the level itself is over 35 that we want to know and report back to the director's office. This is what we think what caused the problem or accidents. So here is a time series, and you can see the concentration in the circle and all the small or very variable size of the triangle, indicating that whether that's coming from the fire detected by these fires are actually the permitted fire by our forestry partner. And we also have a satellite detected fire. I think that's based on the temperature anomaly and stuff. And you can see that a lot of fires in Southeast, as Amber said, are not detectable by satellite because it's really low level and sometimes really tiny. One thing that I want to mention is though that not all permitted fires are actually happening, most likely. I think majority of them are actually happening, but sometimes they change their plan. And then you can see there is a spiky thing going on, but then in fact, these 2 days, the second day is the one that they're exceeding the standard level. So I have a cool animation that I learned that there is a 5-minute interval NOAA GOES 16 satellite image. Then in fact, this one, when we show it to our forestry partner, we actually ended up having better dialogue with them because now you can actually see which point is hitting monitor. In fact, this one that you probably remember that in the time series, there was a peak in the 14. That's caused by this. Then in the night that you saw the huge, a lot more broad hourly the concentration. there is no image available during the night, but we believe that's actually caused by this one above the Macon. So definitely this kind of high resolution temporally, spatially, even though it is just image, if someone come up with the right idea of quantifying PM2.5 out of the image and other information, that's something that we are looking for that will tremendously help us to really pin down what the cause is. So again, that's already covered the story. So again, this is my wish list. At the bottom that I've said that preferably hourly or sub-hourly at 1 kilometer. I know it's maybe asking too much, but I'm hoping that, you know, at one point that we can get there. So that's all.
Thank you for that interesting talk. Our third speaker for the session today is Olivia Sablan from Colorado State.
Yep. Nice. Okay. Hi, everyone. My name is Olivia Sablan. I am a graduate student at Colorado State. University. And I work most closely at CSU with Jeffrey Pierce and Emily Fisher. They're my advisors, and then Bonnie Ford is a mentor to me. So Amber talked about the Flint Hills fires, and I'm going to be expanding on that story, really talking about the ground-based monitoring and connecting that to the culture of fire, talking about a study that our communication students did in the Flint Hills this year. Just wanted to put these names up, these names up here really quick. These are team members, and this project wouldn't be possible without them. Okay, so I wanted to set the stage first talking about the different considerations when talking about rural and urban air quality. So first, let's talk about sources of pollution. Thank you. Okay, so in the rural setting, some major sources of pollution can be from agricultural sources, such as tilling and cultivating the land here. And then in the Flint Hills, we'll be looking at prescribed fires. This is a picture from one of our participants. They took it near their land. And then in urban settings, we're looking at more industrial sources and then emissions from traffic. Also, I wanted to talk about the difference in representation by regulatory monitors in these two communities. This is a picture of the EPA HAQAST air quality system in Kansas, and we can see that these here may be considered more in the rural communities, but the majority of these monitors, these regulatory monitors, are in the urban setting. And then I'm going to be talking later about the perception of risk and benefits. That was what was studied by our communication team. Okay, so this is PM2.5 emissions by fire type. I'm from Colorado, so just contrasting Colorado and Kansas here. So Colorado, we have a lot of wildfires. That's what gains the attention from the media. It costs billions of dollars every year. Luckily this year we didn't have too crazy of a wildfire season. But looking at the PM2.5 emissions from wildfires in Colorado in comparison to the agricultural field burns in Kansas, we see a big difference here. So although these fires in Kansas are relatively small, they emit a lot of PM2.5 and the effect on the rural population there. So this is a map of Kansas looking at census tract. And over here, this is the, oh, I think I have a pointer. Yes, this is the Flint Hills region. You can see it isn't as populated as these other cities, Wichita and then Kansas City up there. And then I'm going to overlay the Flint Hills burning. This is for this past year by the Kansas Department of Health and the Environment. And you can see this relatively unpopulated region has a lot of fires every single year. And this year there were over 2 million total acres burned. In comparison, that's about 3 times the size of Rhode Island. And as Amber mentioned before, wasn't an unusual fire season. There's about 2 million acres burned every single year here. Okay, so this is, again, the EPA HAQAST. You can see they're mostly in these urban regions. But if we look at this video, a lot of the fires occur in the Flint Hills, which is actually where there aren't many monitors. And then we deployed low-cost sensors, purple air sensors. So here are the public purple air that are that were in place before our deployment of sensors this past season. And then here is our deployment. So you can see that we have a lot more coverage, especially in this southeast region. Okay, I think Amber showed this image earlier, but just wanted to restate that this year was usual for fires. We saw about 2 million acres burned, but very unusual for smoke. Again, this is HMS, the Hazardous Mapping System by NOAA. During the burn season, February through May of 2020, 2021, and 2022. And you can see that there were a lot more smoke days this year in comparison to the last years. So how come we're seeing those days? As Amber mentioned, likely from transport. So here is a video of true color imagery from satellites where we can see the smoke developing in New Mexico and then being transported up into the Flint Hills. We can look at HMS for that day. This is a daily average. And there are no local fires here that day that HMS picked up on, but we're still seeing these big smoke plumes overhead. And then there's okay, and then just wanted to show this really quick. This is AOD, so giving a quantitative measurement of what we just saw in the last slide. Transport from Mexico all the way up into the foothills. Okay, so let's talk about our ground-based monitoring. So this is Kansas here, and the different shapes represent our different monitors. So the circles are the purple air that we deployed into the field. The squares are the EPA AQS, and then triangles are the public purple air that were already in place before our deployment. So this is the average daytime PM 2.5 concentrations in micrograms per cubic meter for the burn season this past year, February through May 2022. And then we're going to compare that to PM 2.5 daytime for non-smoke days. How do we determine that they're non-smoke days? Via HMS smoke plumes. And then comparing that to days with any type of smoke. We worked with Emily Gargolinsky to determine the different types of smoke. So there's transport smoke days as well as local smoke days. And then you get some days where you have both local burning as well as this transport. This is any type of smoke here. And there was about a 50% increase in comparison to this non-smoke day where we weren't seeing any plumes to days with any type of smoke. Okay, and then I wanted to bring it back to looking at the differences between the rural and urban communities here. So I labeled any sensor that was in close proximity to cities that had populations of 100,000 or above. So you can see here, this is the rural versus urban monitors, and then tease that out into smoke versus no smoke, again from HMS plumes. And you can see that these areas actually experience pretty similar PM enhancements. In the future, I'm hoping to combine AOD as well as these ground-based measurements to make smoke exposure maps. That's where we're going in the future. We are having a hard time with all the different types of smoke that we're seeing. The transported smoke's making things difficult, as well as the clouds. It was very cloudy this season. And then Emily Gargolinsky talked a lot about the dust. So we will look into that moving forward. Okay, and then briefly wanted to talk about the communication study that was done by 2 graduate students on our team, Zoe Rosen and Giovanna Henry. They interviewed 18 participants in the Flint Hills of Kansas, and this map represents the counties from which those interviewees were that they resided in. And this was conducted this past burning season. Okay, so they asked these participants in the interviews how they knew when burning was occurring in the Flint Hills. They commented that it was mostly environmental from cues like sight and smell, as well as a social word of mouth / knowledge of the season. And then they asked them what the effects were seen from this burning. They mentioned that it boosts cattle weight gain when they burn the grass and it grows back. The cattle feed on it and they're able to gain more weight from that. And this is also a local cultural connection to fire in the region. And then looking at the difference between the rural participants in the interviews as well as the urban participants, the rural participants mentioned that the risks with burning, they thought to be mostly associated with a threat to life and property with these prescribed burns getting out of control. And they also commented that there are threats if they don't burn to the ecological health with the tall grass prairie ecosystem in that area. To contrast this, city participants said the threats that they considered were mostly the threats to their health by being the downwind communities, although as I showed before, their smoke exposure is fairly consistent in both regions. And I'm just going to put these key takeaways up here if you'd like to read. Future steps, as I said, is combining those ground-based surface measurements with satellite observations, and then working with Emily and Amber to connect smoke with fires and then bird skies as well. Thank you.
Thanks. Thanks, Olivia. And our last speaker for this session is Libby Mohr from the Environmental Defense Fund.
Thanks. So I'm Libby Mohr. I'm a data analyst with Environmental Defense Fund, and today I want to talk to you about our interest in formaldehyde as it relates to emissions from petrochemical facilities, and our interest in using satellite data to inform both health risk and identify sources of formaldehyde. And so I'll start with just an overview of our petrochemicals initiative. And so petrochemicals, whether or not we realize it or not, are really just a part of our daily lives. They're used in the production of everything from plastic to synthetic textiles to fertilizer that grows food. The global petrochemical industry is huge. It's valued at about $550 billion with $400 billion of planned investments in new facilities. Unfortunately, petrochemical production comes with some societal costs. And so these facilities are emitting a slew of air toxics that could be really hazardous to the communities that live nearby petrochemical facilities. And so our aim with the Petrochemicals Initiative is to really improve the health and well-being of communities that are overburdened by toxic emissions from petrochemical facilities. And we're focused right now a lot on Texas and Louisiana, just because that's where a lot of these petrochemical facilities are located. And so I just wanted to note, because this is the rural session, that petrochemical facilities can be found in a variety of settings. And so on the left here is an example of a petrochemical facility in more of a rural setting. This is located between Baton Rouge and New Orleans in Louisiana, in an area that's been deemed by its residents Cancer Alley, and because of the high prevalence of cancer and petrochemical facilities in that area. On the right is an example of more of an urban setting of a petrochemical facility, which is along the Houston Ship Channel. And so our interest in formaldehyde as it relates to petrochemical facilities stems not only from primary emissions of formaldehyde by the facilities, but also emissions of chemical precursors to formaldehyde, like ethylene, propylene, acetaldehyde, 1,2-butadiene, and isoprene. And so this map here on the right shows summed formaldehyde and precursor emissions in Texas and Louisiana from the 2020 toxic release inventory. And you'll notice that a lot of these emissions are clustered along the Gulf Coast and also in this area, which is Cancer Alley. And so outdoor formaldehyde exposure really presents a substantial cancer risk. And so this map is showing cancer risk estimates from AirTox Screen, which is a model that uses CMAC to estimate formaldehyde concentrations, and then it uses exposure modeling to estimate cancer risk. And so it's worth noting that because there's all of this modeling, and these numbers here are only as good as the assumptions in the models are good. And so we kind of take them with a grain of salt and use them more to understand relative cancer risk. But you'll notice there's a large hotspot here, and that's likely due to biogenic emissions, because that's a very forested area. Some of the cancer risk is also coming from VOC emissions from mobile sources. But inevitably, some of this cancer risk is coming from emissions from industrial facilities, and because air tox screen is at the census tract scale, it's likely really underestimating the really local cancer risk that neighborhoods that are right next to petrochemical facilities are experiencing. And so formaldehyde is not only cancer risk is not only noteworthy on the absolute scale, but also on the relative scale. So this histogram shows that in the majority of census tracts, the fraction of cancer risk from air toxics is greater than 50%. And so formaldehyde is contributing a lot to cancer risk from air toxics exposure. And at the same time, ground monitors are very sparse. And so there are just 132 monitoring stations in the continental US in EPA's ambient monitoring archive. And in 2018, only 102 of those monitors had data coverage for more than 9 months of the year. And so you'll notice that there are even entire areas of the country, like down here in the south, that are just missing monitors. And this is likely because new monitors are expensive to install and really labor intensive to operate. Oh, thank you. And this problem is particularly bad in rural areas. And so this plot is showing on the y-axis formaldehyde and precursor emissions on a log scale, and then on the y-axis population, or on the x-axis population density, also on a log scale. And each one of these points represents a single county, and only counties that have formaldehyde or precursor emissions are shown on this plot. The color of each point indicates whether or not a monitor is present in that county. And just for reference, I wanted to point out Dane County, Wisconsin, which is where we are currently located in terms of getting a sense of population density. So what you'll notice is that most of the monitors are sort of in counties that have population densities greater than 100 people per square kilometer. But a lot of the counties with emissions are less densely populated than that. And so this really illustrates that less densely populated areas are less likely to have monitoring, even if their emissions are just as bad as some of the more urban places. And I just want to point out these 2 points as sort of case studies. These are counties that are near or on the Gulf Coast of Texas. And you can see that they have particularly high emissions and no monitoring. So just to kind of make this point again, this ground monitor network is really missing several areas of high emissions. And so there's emissions closer on the Gulf Coast and in Cancer Valley, but there's really only monitoring in Houston. So we might turn to a model. And if we did, we might find that that air tox screen is systematically underestimating formaldehyde concentrations. And so here, the green points represent annual mean concentrations from 2018 measured at the ground monitors. And then these purple points represent the estimated concentration of formaldehyde, the annual mean. And that's from air tox screen, which uses CMAQ again. And so what you'll notice is that the air tox screen estimates are consistently lower than what's being measured at the ground monitors. And there's a couple reasons that we thought of that this might be. I'd be curious to hear what you all think. One of them is that there's a lot of uncertainty with emissions inventories, both biogenic emissions inventories and anthropogenic inventories. The second reason is, as I mentioned before, air tox screen is modeling on the census tract level, and the monitor is located at a single point within the census tract. And so it's possible that the monitor isn't necessarily representative of the census tract as a whole. And so given, sort of the sparsity, thank you, of ground monitoring and the limitations with models, we're really interested in the potential for satellite data to provide insights into identifying anthropogenic sources of formaldehyde. And so we've sort of identified a couple of key challenges with doing this. So our first critical need is methods for separating anthropogenic biogenic emissions. And this would be really important for helping us to understand, how much of this formaldehyde exposure is preventable versus, just coming from isoprene emissions from trees. Our second critical need is oversampling the satellite data for better spatial resolution. So if we want to understand, or if we want to identify specific facilities that are emitting formaldehyde and its precursors and causing these hotspots, we really need a better spatial resolution than what you can get out of the box, and even at the expense of temporal resolution. And so we're interested in oversampling methods for getting, maybe annual mean concentrations of formaldehyde or vertical column densities of formaldehyde at a much finer spatial resolution. We're also interested in using satellite data products for assessing health impacts of formaldehyde. And so the critical need here, thank you, is we're interested in methods for taking vertical column density and using that to estimate surface concentrations to understand what people are actually being exposed to. And so moving forward, we're really excited about the enhanced spatial resolution of satellite retrievals like those from Tropomi and eventually Tempo. And we're excited about the enhanced temporal resolution of Tempo. And we're hoping to move forward by comparing formaldehyde columns from Tropomi and eventually Tempo with the ground monitoring data, and starting with the pseudo Tempo data from the TracerIQ flight simulation over Houston, which is an area where the city and the county have additional monitoring, and we're interested in partnering on this. So just to sort of sum up, we're really excited about the potential to leverage findings from these data-rich areas like Houston to allow us to then make satellite-based inferences in data-poor areas and rural areas like Louisiana. Thanks for listening.
Thank you, Libby. And now I'd like to invite all of our speakers to come up to take a place at the front, and time for some questions.
Yeah, I don't know. Here, I'll make it symmetrical. Then we can be by the mics too. Oh, yeah, that's good. Is it on?
Playing musical chairs with too many chairs.
Oh, yeah, it's on.
Okay.
Exactly. It's the wrong way to play.
Yeah. So we have a couple questions from the chat. And maybe just to get things started before I have a chance to look at them, I'm wondering, and this is primarily for those that have been studying PM, what can we say about what's happening at the ground in rural areas, particularly when we're dealing with long-range transport and when we're interested in short timescales? So I understand Calliope offers this sort of profile information, but it's sparse. And when we're dealing with long-range transport, there's injection height oftentimes that's playing a role that leads to some ambiguity mixing down at the surface. We have columnar observations that are representing a column. What are the ways forward in terms of representing that? And I'll open that up to all of you.
Me first. The ways forward. I think that also goes to the wish list question too, doesn't it? I think that we're doing a really good job of improving the satellites. Like GOES is now 2 kilometers and it's every 5 minutes. That's pretty incredible, but it's the horizontal, not the vertical. In terms of Calypso, that is going away, so we're not going to have another space-based LiDAR for a while. But if you look at 2 columns, let's say the vertical over the United States, and this one is, you can see the smoke being transported from one place to the other. So you don't necessarily need to be right near it. So it's less sparse than you think it might be if you can get, so you'll need one, and that will verify models. So you also need the models. So that's another way to get at it. I think that well, because I know Calypso, I don't think that we've done enough to really to use that data yet, because it's complicated for the reasons you mentioned. So it's not right near a fire. We have Miser and then we have Calypso. So it's not right there. Miser would be better at that, but it's kind of far away, but we have models to pull it all together or to backtrack it. So perhaps something that can be done in the future is to better look at all the Calypso data in order to say, what was the fire weather? What are the fuels? What is the ecosystem? And what is the injection height? Dependent on all of these things, and establish these relationships better to improve our models, because you're just not going to pull it together without models. And so that's a request, it would be great if we could have the 1 kilometer goes overhead. And it looks like we're moving in that direction.
Thank you.
I think I can second for the parts for the modeling. We've been using, say, the high split trajectory mode so far. And I know that there is a dispersion mode of a high split, for example, which can be better characterizing the dispersal of the plume from the origin. I have not seen a lot of usage of yet or use case for some reason. I think that might be one of the directions that we can utilize existing technology that we already have, although I have not been using, or my team has not been using it. But going forward, that kind of, existing tool, utilizing more, that's one thing. The other thing may be like the second about the utilizing more model about it. Oftentimes those trajectory model had a hard time to kind of tracking the air mass that's turning over the area. It just has a disconnect, obviously. So maybe going forward, that if there is a kind of online or pretty close to near time, I guess a blending technology that's taking the satellite data with possibly the either forecasting or hintercasting dispersion mode of the meteorology model, to blend it readily available for the agency to use. I think that will be very helpful. In fact, when we had the short chat with our forestry folks, that they already have sort of the setup system, even had a specific term like a transport wind to decide what they want to do for the burning or not. I think if the community can provide a little better, again, resolution and accuracy data to help their decision making, even for the prescribed burn, I think that will be also helpful for the area agency going forward.
Yeah, I can just comment on this a little bit. As I mentioned, we had a couple challenges in the Flint Hills this year with the transported smoke, and then also we're having issues with dust, and then bringing that in the cloudy days. It's hard to determine via HMS, if there are plumes, if this is local fire, if this is transported. So grateful that we have the ground-based monitoring to know that, even when it's completely cloudy for most of the day, we're not seeing any fires or smoke by HMS. We can't really see any AOD via satellites, via GOES. We know that on the ground, there's still elevated PM concentrations. So yeah, we're still working on that and overcoming those challenges there.
Thank you. Is there any questions in the audience? Over here.
Yeah, this kind of goes to Olivia and Amber primarily, but yesterday when Emily made her presentation, I asked, what's polluted dust? Okay, and then it occurred to me later as I was thinking, we had kind of an unusual event. I live in West Texas, and we had a big brush fire out there, which is grass and junipers and everything else. And the atmosphere was conditionally unstable. So this heat at a point caused enough thermal lift that a big cumulus cloud formed and then moved downwind. Well, it started to rain, and one of my cohorts the next day showed up at the office with a truck that was covered in ash. So I wonder how much of what we're perceiving to be dust from the satellite signal might actually be ash that's lifted in some of these smoke plumes. And I'm wondering if there was any other evidence of that from Olivia's colleagues that interviewed the people out there in the Flint Hills, if that was a usual occurrence.
There weren't many comments about ash this year, specifically talking about the participants from the interviews. But they did notice a lot of dust, particularly because I think Emily talked about in her presentation that it was a very dry year. There wasn't much rain and a lot of severe winds, which kicked up a lot of dust.
Yeah, we asked the same questions because I mean, we're on the same Tiger team. So we're like, oh, okay, well, let's look into that. And you guys look into this. So it's pretty awesome, I think. And I remember, so we were hearing from the people in the state, but also we heard from the interviews. Oh, no, fires are about the same, but there's sure a lot of dust. Not, you know, so that's what they said. So finding that in the satellite data was fantastic. The other thing that I'd like to say is, if you look at some of the basic research, there, every fire, whether it's agriculture or a large fire, as it rolls through, it's going to stir up soil or granite matter, so dust. So every fire is going to have dust. Every single one has it at the fire front. It's measurable. But when you have a drought and a lot of wind, that's a lot more dust combined with the wildfires, combined with the prescription fires. So at least in terms of dust, it was an unusual year. Drought, dust, wildfires, wind, and that's any way you look at it. Satellite data, people on the ground do a really good job.
What about the temporal disconnect between the fire and the dust? Because we've seen otherwise stable ecosystems out in West Texas. After a fire goes through, there's sand blowing everywhere.
Yeah, that makes sense because they burned off everything that holds it in place.
Right.
So that makes sense to me.
Well, was there a temporal disconnect in the Flint Hills this year?
We didn't see that. And I haven't asked our colleagues. We could ask, they didn't write to us like they did before. It's like, a big drought, lots of wind. And we didn't see that like in May. So we didn't hear that. But I can imagine it if you don't have much vegetation. On the Flint Hills, they've been burning for a long time. So, you know, they have to.
Sure, go ahead.
Yeah, for the regulators up there, but you know, I'm gonna get, but the thing is, curious, these prescribed fires, even the Flint Hills, have they needed to flag the data? Has it come to the level where it might be an attainment issue, or is it just a health issue? Because obviously you don't want to be smelling smoke, but what do the state officials really do about it? Anything?
I can speak for Georgia. We like explained that we come up with the excellence report that goes to the director, and like you probably hear about the exceptional event that you got to have some sort of the hurdles that we have to go through. That was sort of fortunately we didn't have to go through recently. That's where we are for now. But I guess add one more or repeat the thing that I shared the first day. Now that you can imagine that the hourly data that's actually coming from the FEM monitor that as I shared, that there is a little bit of discussion, well, not really a little bit, but discussion going on about the FRM versus FEM, about especially these fires has a lot of organic compound in it. But we kind of sense that it may have a high bias for this. So that has if it gets accumulated enough, then it has a huge impact on the final design value. So that's where we are working on. But yeah, as of now for our state, that we're just at this stage kind of keep tracking it.
I don't know that if Olivia and I have really talked to the regulators yet, but because, I mean, they're burning, and on the cloudy days when you see a lot of clouds, which goes to the previous question, that's our Olivia's statement. Actually, they're going to light fires then because they like to do it when it's cloudy because there's less heat and more chance for control. So they are going to light a lot of fires then that you can't always see from space. So that's when they're going to do it. But I think that as far as regulatory monitors, I learned from you, all of you, is if you need so many days and they're not burning that many days in a row to go in exceedance, then it wouldn't be flagged, would it? But, you know, I'm not a regulator and I wish that I had learned that information. I don't know if Olivia has looked at that regulatory questions. in the Flint Hills?
Looking at regulatory monitors,
Pardon me?
looking
Yeah.
at regulatory monitors.
Well, or purple air, or did they flag anything?
No,
Did our-
there was no plug, and they're not in non-attainment in my understanding, at least for PM 2.5.
It looked like there was some non-attainment. No,
Was there? I don't believe so.
no, but it was only days, not,
You need 8 days of continuous monitors.
yeah.
Well, one thing that I guess reminds me that I probably need to share is that because of this image and everything that we've been analyzing, we had a dialogue with our forestry partner that they've been working on this too, but you can see that as I shared, that when you start burning things very late afternoon, that it gets trapped in a low PBL and eventually kind of thicken. And then when you hit the monitor, it hit really hard. So one of the sort of suggestion or recommendation we were making was, if possible, then start burning a little earlier when the mixing height is a little high, so that it doesn't get too concentrated when it's it has to monitor. It's not just a measuring issue. In fact, if it is at node level, that actually related to human health. So that's the kind of timing of the fire is also another aspect of it, although it's not really sort of a regulatory per se. We've been working with our forestry partner about it.
Thank you. I'll see another question at the back.
Yeah, I'm just curious about how you're using satellite data. So I saw like different groups of true color RGBs. I'm curious if you've also looked at the different like fire RGBs, dust, ash RGBs, and if you find any of them useful.
We did not specifically look into it yet. Part of it is also, we've been kind of struggling with whatever we can get right now. And I guess I'll look into it further, but I guess the information at least that I heard is that like Amber shared and we have been seeing, and also the fire map that I shared with, these are really small fires. Some of these fires are like less than 100 acres at most. So yeah, I mean, if they can catch those low fires that sometimes under the canopy, then why not? We can use it. But so far, we found that relying on that permit database with some other analysis that we've been doing was sort of the optimal analysis. But definitely, if there is a better source, then we'll look into it.
Great. Well, there's the lull in questions. Jennifer offered to read one of the first questions from the chat.
Okay, so Amber mentioned that there's a larger tiger team study on agriculture fires in the Southeast. As a Floridian, I'm curious to learn more about this study and what findings her team anticipates as compared to the Flint Hills study, particularly given that dust and wildfires that plague the Flint Hills region are not likely to be as impactful to the Palm Beach study.
That's true. And he had, I don't know, do we know if the HAQAST posters are gonna go online? It would be good. Okay, all right, Kellen is shaking her head. And Kellen and the Colorado team have just gone down to Florida and put the purple air monitors out there. And they are the better people to answer this question. The whole mode has changed, like the social questions have changed. And I'm just very excited to be a part of it. So Emily and I are going to do the same things. We're going to look at the inside, the outside. Is the smoke coming from inside? Is it going to come in? So we're doing the science and how do we actually, for Florida and thinking about small fires, perhaps in Georgia too, to quantify how much can we see with satellite data? So what do we see with what satellites? So to quantify what we're missing and to put error bars on that, which should be helpful. So we're going to do the same thing. But the rest of the team has just gone down there. It's totally different. We'll say socially, particularly, it's different. And I don't know if Kellen I don't want to step there. I would like for Olivia or Kellen or somebody, we're just starting.
Yeah, I could
I
talk
care about
about,
science.
because I think the question was also, the challenges with dust that we saw in the Flint Hills. We're not going to see that in Florida. A challenge that I foresee that we're going to get to in Florida is with humidity. Purple air is known to have bias when there are high humidity. when the relative humidity is high, sorry. So we will be using correction factors, hopefully, to kind of mitigate that challenge there. Another challenge so far that I've seen is Florida is also going to be cloudy. That will be a struggle with our satellite data. I hope that answered that question.
Thank you. Question from the front.
I have a question for Libby. I'm wondering about your thoughts on the feasibility of using these satellite-based formaldehyde estimates for quantifying overall exposure to hazardous air pollutants and the overall cancer risk. I think there could be a lot of interest in that if you think that it's feasible to use that.
Yeah, I think that's a really good idea. I think it could be possible to look at correlations between different air toxics, because there is ground monitoring. I think the challenge would be that there are so limited, there's such a limited number of formaldehyde ground monitors, and we need to find formaldehyde ground monitors that are co-located with monitors that are measuring other air toxics, so that we could build the correlation and sort of see if formaldehyde, that's a good idea. Thanks.
Before we go, can I ask, because you're not talking as much, also Yang was showing that formaldehyde was also very often attributable to fires, and I didn't realize that as much. So I don't know if you're putting those together or teasing those apart, so that, the formaldehyde in cancer, it's scary.
Yeah,
And Louisiana has a lot of farm burning.
for sure. Yeah, that's a good flag too.
Oh, okay, good.
Yeah, there's
Yeah.
lots of sources. I think there's a
Question first from Arlene, and then
Yeah, I was just gonna build off that question too. I was wondering, I mean, I appreciate that ideally you have monitors so you can kind of build those relationships with other groups that aren't necessarily gonna be visible with statements like humans, if that makes sense. So, but I'm wondering, like, on the emission side, how well understood are those co-emissions? Because maybe that's another possible way to bring different data sets. I'm thinking in particular about, like, Daniel Tom's like 1 kilometer inventory that has lots of details about the individual sectors. So if you could feed that into a model and you trust the emission, maybe from there you could build that forward.
Right. So yeah, that's a really good point. I have been digging into NEI, and also, so there's NEI and then there's TRI. And with NEI, which is the sort of emissions inventory that goes into CMAQ that makes air tox screen. A lot of times the VOC emissions are just in NEI as VOCs, and then they have to get speciated into the different chemical precursors to formaldehyde or different air toxics. And I think that there's a lot of uncertainty with that speciation process. So I think it would be tricky, but I think that's a good idea to sort of leverage the emissions inventories, which are also challenging because they're both because they're facility reported, and so they're hard to verify, and also because I think it's just really hard to quantify, like, fugitive emissions and the different types of emissions.
Are there any new improved sites coming your way, the EPA, the new sites that are coming out? Because there was a big hole in your area.
I haven't seen that, but I'll have to look into that. Yeah.
question from you, yes.
Yeah, this one's for Libby. You said you're trying to disentangle the industrial emissions from the biogenic emissions. I was just wondering if you thought about looking at the period during the beginning of the pandemic, because I know living in West Texas in a town with a refinery, basically the stream of petrochemicals going through these refineries just stopped.
Oh, really?
The tanks were full. They had no place to sell it. Nobody was buying it. And so there was a period of time there where there was very little petrochemical activity.
Huh? Yeah, that would be interesting to look at.
So you might be able to see a difference in the average of previous years to 2020 in the spring months.
Right. Yeah, that's a good point. Yeah, I think the other challenge is separating the because there's both the industrial emissions, the biogenic emissions, and then there's now fires and mobile sources. And so
well, the mobile sources were pretty much shut down too.
Yeah.
Nobody was buying fuel because nobody was going anywhere.
Right. Yeah. Yeah, that's interesting. Should look at that. Thanks.
Okay, while there's a lull, there's another question in the chat that Jennifer can read to us.
As Amber and Olivia alluded, research has shown that grasslands are one of the most endangered ecosystems in the world, primarily due to the loss of fire alongside climate change. Fire is critical for the ecosystem alongside preserving the economical benefits for rangeland use. An ask for researchers like HAQAST is how can we leverage satellite data to support prescribed fire use, which is only anticipated and needs to increase.
Oh, me. Yeah, you. So, and looking at, I can think of a couple things, and I'm just thinking off the top of my head, could be wrong. That's a big question. And listening to the group from Colorado, and they did the social questions. And so the people on the ground in urban areas said, oh man, that pollution's really bad, but they didn't have any kind of connection to fire or the ground. So they were thinking in terms of health, which is fine. That's the way they were thinking. And then the people that lived in the rural communities that were burning and that had cattle that had died because they didn't burn enough and fires got out of control. I mean, it's very emotional to lose your home that you've had for generations of cows, generations of people. It's emotional, it's painful. So they have a true connection to the ground and a cultural understanding of the fire and what needs to happen. So even if these social questions come out and the city people know more about what's happening and why they're burning, and if they understand and possibly could do something, if the farmers, ranchers, and people that do prescribed fires could learn more about what's happening in air quality, how the smoke influences, and we lost them, Michael Geigert from Connecticut, he has big ozone problems because of the burning in the foothills. Do they know about that? Probably not. So he doesn't meet exceedances. He goes over exceedances because of the burning in the foothills, and that's in Connecticut. So if they knew about that, maybe some things that we could do, and I'm just making this up as I go along, instead of burning all in April, why can't we do a little bit more on the end so that there's less smoke over a longer time, and possibly have some green season burning? I mean, I don't have any of the answers here, but if we could just talk to each other, and this is what this kind of research does. It's the science, and we'll do the science and figure out what the error bars are and help with that. So that hopefully helps people in the communities that are doing air quality regulation in Kansas and the Flint Hills, but also at the EPA, and then just the social aspect, knowing about each other and starting to ask the questions. Okay, well, we need fire. If we figure this out, what can we do? Air quality monitors for people in schools if you're in poor regions, and that would also be true in Florida. So if air quality is really bad, how do we protect the vulnerable populations? So I see all kinds of answers, and sometimes asking the question, which is not true for the Flint Hills, but are we really burning for the right reasons? Is my soil really better if I burn after this, or is it hydrophobic? Am I doing what I think I'm going to do? Is there a different way? So if we all have to give a little, I think that that's something that comes from this interdisciplinary research where we all learn something.
Great. So we have 5 minutes left, time for one more question. There's one more in the chat, so I'll just check in the room first. Okay, no burning questions in the room, then the last one from the chat.
Questions?
Yeah.
Unintended.
Smoke often gets compressed with nighttime inversions, leading to higher monitored concentrations. Is there a way to detect that increase in concentrations using satellites?
So yes, but it would have to be overhead, and it's very, the swath is only 100 meters wide. It's not that wide, so it's not going to be over that often. So we, in order to make statements, we use all the data for the Flint Hills over a longer time. So it's return. It's a polar orbiter like photospheres, like all of those, it's on a polar orbiter. So, but its swath width is not wide, it's very narrow, so it doesn't, what are the chances that you get over there? But that's one way. Also, not from space, but there are LiDARs that the EPA has and other people have that could look at the vertical profile. Monitors are at the ground. It's often, and Calypso LiDAR is better at night than it is during the day. There's all kinds of stuff in the air during the day, so it does a better job. So when you said night, that made me think of that. So I think ground-based monitors and more of them as we get better to calibrate. I'm not so sure that we're going to be good at that at night. Fires you can see at night with GOES, FIRS, and MODIS if they're overhead and depending on how big they are.
Yeah, just to add on that real quick, we were seeing quite a diurnal cycle with the ground-based monitoring. So there was elevated PM concentrations into the evening and nighttime. We're going to look into that further, but unfortunately we can't use satellites, at least GO is what I use, to look at that nighttime elevation.
So I want to convert that question to my another wish list that I would like to have that kind of satellite product. Especially at nighttime.
The other thing is models, the modelers. I mean, it's critical because so I would think field campaigns, aircraft campaigns that can fly over places that are like this, field campaigns, aircraft and models. So if we can put the information that we have with field campaigns together with the models, because nighttime emissions, no matter what it is, that's really challenging.
Okay, well, thank you very much for an engaging session. It's been a pleasure to hear all the questions and the exciting comments, and thank the panelists once again. So thanks, everyone.